a few things about heat engines and what happens in heat engines, how they work, what is the physics of heat engines. We will not go into the engineering of heat engines. That we will leave to engineers. And try and see the basic principles behind them. That will lead us to a better understanding of the laws of thermodynamics. How do we visualize thermodynamic processes? Let me start by saying that, we often talk of thermodynamic processes क्या हो गया आज बड़ी मरमर है कोई बहुत एक्साइटमेंट है आज क्या हो या कुछ हो गया आने से पहले हैं अच्छा all right thermodynamic processes are essentially those in which your system faces changes in thermodynamic parameters like volume, pressure, temperature, and then also heat is exchanged and work is performed. Heat is either given to the system or system gives off heat. Work is either done on the system or the system performs work on its surroundings. So we have therefore such thermodynamic processes, and we need to sort of visualize these processes. Not very difficult to visualize, but let me still try to do this so that we keep this in mind when we try and look at heat engines. Visualization often goes in the form of for example, a cylinder and a piston. Cylinder may have thick walls, may not have thick walls, but you have a cylinder and so there is a volume here, and there is a pressure here, and there is a temperature here, and maybe the system can exchange heat with surroundings, and as it moves up, out and in, it can perform work. Another way of writing this, doing the visualization, is to assume a cylinder sitting over here, a vessel or a cylinder, with another movable piston, and then the cylinder can sit on top of a heat bath. The heat bath, the surface connecting with the heat bath is conducting so that heat can flow in and out. Heat can be given to the heat bath, heat can be taken out of the heat bath. So this is a source of heat going in and out. And the piston moving up and down is the work that the system does. You can apply pressure onto this system by putting in some weight on top, and system temperature and volume will change as we change pressure and as we supply heat to the system, and that is how we will calculate the amount of work that is being done. One important thing, या आपने चॉक्स का बंदोबस्त नहीं किया, सफेद चॉक्स का।
तो सर हमने आगे कंप्लेंट इसी वक्त कर दी थी, मगर उन्होंने कहा था कि अभी मिली मार्केट से नहीं मिल रहा।
अच्छा, मार्केट में नहीं है भाई चॉक्स। अब हाथ के इशारों से बातें करेंगे आप लोगों से, हैं? चॉक्स यहाँ हैं तो बहुत, मगर ना लिखने वाले चॉक्स हैं यहाँ। And in this case, we must understand one important thing, that there is always a working substance. Working substance is the one that takes in heat, and that is the working system that experiences pressure, that experiences temperature, whose volume we measure, which takes in heat and which performs work. This working substance can be gas, can be liquid, and in some cases can be solid also, but then that will be difficult to visualize, so we will just, जो वही हैं जो मैंने अभी लिए हैं वहाँ से, वो तो वैसे ही हैं. Okay, we will see. Working substance, we have always to remember that there is a working substance in these gadgets, in these things in which we perform thermodynamic work, processes. All right. Let us try and visualize a heat engine. And I am saying a heat engine because there can be heat engines of various kinds. One very simple heat engines. One important term that was used by Kelvin, I will use Kelvin's words, which he called it self-acting engine. Because the word automatic was still not in use so much at that time. So, nice word that he coined, self-acting engine. So the machine that we want to, or engine that we want to invent must be self-acting, must be automatic, must be able to continuously move, continuously perform work. It shouldn't be that in each cycle we take the machine and perform work on it again and have to continuously work on it. It should be self-acting. It should be working on its own. It should be an automatic machine. This is the purpose of devising the engine. And for this machine to be self-acting or automatic, it will have to work in a cycle. It must work in a cycle. It should sort of do some work and then come back to the initial state. So it should be an initial state, then maybe to some another state, and then to another, and then to another, and I don't know how many times, however many times, eventually it should come back to the initial state. So that it can start all over again. So it has to work in a cycle. The process that we must define must therefore be a cyclic process. the machine that we want to define, engine, must take heat from a source perform work and then in addition to getting back into the initial state, it may not be able to perform to convert the entire heat into work, so it should be able to throw away the rest of the heat somewhere. So and throw away remaining heat, excess heat. This is the cycle in which it will work. It will have to be connected, therefore it should be connected to two heat baths. I used the term reservoir in my first lecture. The alternative term is bath, heat bath or heat source, heat reservoir. So the machine will have to be connected to two heat reservoirs. This is how we are visualizing a machine. And now we will say, because the state of a system machine is given in terms of this pressure, volume and temperature, and pressure, volume and temperature defines actually the our normal thermodynamic space. So we have therefore volume here and pressure here, and we have temperature on this side, but then visualizing a three-dimensional picture, or at least drawing a three-dimensional one is a difficult thing. So what I will do is I will take projections of temperature things onto this, and I will say that we can draw these isotherms on this to define our temperature scale. So here I have therefore these isotherms. Okay? Isotherms are the lines on which all the points on a line are at the same temperature, and T1, T2, T3, etc. are such that T1 is less than T2, is less than T3, is less than T4, and so on. As you go out, you are at a higher value of temperature. And here we will define we will try and make a convenient, make a convenient heat engine or cycle. I will start from anywhere here, for example, starting point A, and I will keep volume constant at this level and increase the pressure. Keeping volume constant, I will increase the pressure. That will take me to a higher value of temperature. Okay? So the first thing is, I will keeping V constant, increase pressure. All right? I can, in that box over there, what I will do is that I will increasing pressure amounts to saying that I will add more weight on top of it. And but I will add more weight on top of it, but by adding more weight, the volume will decrease, so I will supply heat to it so that volume doesn't decrease. So I will supply heat to it, and I will, so in this particular process, system will receive heat from outside. Okay? And then I will, I have to draw these things in a clever manner. So I will draw another isotherm over here because I will need it. So I will then keep the pressure constant. Increase volume. Keeping pressure constant, increasing volume amounts to also increasing the temperature. The first thing also increase the temperature, raises the temperature. It raises the temperature from T1 to T1 to T2, yes. Right, the first step, increase the temperature from T1 to T2. Now I keep the pressure constant and increase the volume. When I do this, temperature also increases, and this temperature, and actually this volume can be increased by keeping pressure constant. If I supply more heat to it, I will call this heat therefore Q1 and this heat Q2. And this volume increases, heat comes in, and temperature rises from T2 to T4. T5? Oh, T5. Okay. And then I can visualize coming down. Again, keeping V constant, I decrease pressure. Decrease pressure. When I decrease pressure, I will actually also decrease temperature. Temperature goes down from, and actually in this particular process, when I keep volume constant and decrease pressure, heat will be released, heat will go out. And temperature also goes down. Temperature goes down from T5 to T3. And then lastly, I will go from this point. Let me label these points, okay? Now I think I'm in a position to label them. I'll call this point B, this C, and this D, and it will from D to, it's coming down from D to A. So this process A1 was A to B. I'm writing too small for the people on the back side, right? It won't get any worse. So can I continue, or shall I change to a, I think this will be fine for this part, and then I will make sure that I don't write this small. Keeping V, now this time I'm keeping P constant. V decreases, and temperature also decreases. Heat leaves the system, and temperature goes down from, temperature decreases from T3 to T1.
So where does the heat go from inside the system?
Okay, so now we have therefore Q3 that is going out and Q4 that is going out. Q1, the question that he asked is, where is the heat going in all this particular process? Okay, so as you said, there are these heat baths from which system is getting heat and to which system is rejecting heat. So in process number 3 and 4, system is giving out heat to one of those heat baths. Okay. Now in process 1 and 2, it is taking heat from outside. And then what is happening? Where is that going? Not all of it is being thrown out. If all of the heat that is taken in is thrown out, then the system is not doing any work at all. We want work out of this machine. And therefore, the answer to your question is that heat gets converted into work. And that is what the whole machine was supposed to do. Okay? All right. So this is a simple design of a machine which can work in this manner. And here in this work, I will try not to write, this is small now. In this work, we have actually, you can see that there are in steps 1 and 2, heat is entering the system. In both the cases, temperature rises. Once it keeps volume constant, the second time it keeps pressure constant. Correct? In steps number 3 and 4, in both these processes, heat leaves the system. Temperature in both the cases decreases. In one case, it keeps volume constant. In the other case, it keeps pressure constant. So all of this is fine in the sense that the first condition that we wanted to put in for, as Lord Kelvin said, it should be self-acting, it should work in a cycle. We have brought it back to the original point. Okay? We have taken in some heat from outside and we have done some work. We will calculate the work and then we have thrown out the rest of the heat. How much? Okay. Convention was that Q that goes into the system is positive. Q1 goes into the system, Q2 goes into the system. Q3 leaves the system, so it is negative, and Q4 leaves the system, therefore it is also negative. Let's see. W1 and W1 is work done while it is doing this. Work done is minus PdV. So minus PdV, this is 0 because dV volume doesn't change. Similarly, W3 is 0 because in this process also volume doesn't change, system is not able to perform any work. W2 is simply when pressure is constant and volume changes, isothermal process. This is, no, we have said temperature rises, okay? So we have not said it is an isothermal process. So this is actually a process in which the system actually at a constant temperature, at constant pressure, the work done is minus P times dV, which is minus P in the first case, P2. The pressure is PB, and in this case pressure is PA. So PB times the difference in volume, which is VC minus VB. and W4 is equal to W4 is equal to minus PA times V A minus VD. And VA is the same as VB and VD is the same as that. So this is actually equal to plus PA times VC minus VB. Okay? Because I have, for my convenience, taken this to be a rectangular process, completely rectangular process. Which certainly I can, in practice also. And therefore, W2 plus W4 is equal to this plus this is PA minus PB times VC minus VB, and this is VC is larger than VB, so that part is positive. PA is smaller than PB, so that part is negative. So this work, total work, is negative. And remember our convention that then when system performs any work, it is negative. So the system is able to perform this work. The amount of work it has been able to perform is equal to this. Okay? This is actually area under the curve. Because you went from this point to this point first, and the area under the curve is just this. And then this is W2, and W4 was from here to here, which was this. So you subtract, this is the work done by the system, the first one, and this is the work done on the system, and the total work, remaining work, is this. So this is the total work that the system did on the surroundings. Okay? So the work done is equal to this, and total, this is what the system did. Okay? We can also then write down the efficiency of the system. Efficiency would be, you would say, how much work was it able to get done by the amount of heat that it received. Okay? This will be the work done, efficiency of the engine. And the work done, because since cyclic process, therefore du equal to 0, no change in internal energy, because internal energy is a state variable, a state function of the state. Therefore, over a cycle, there is no change in internal energy, and therefore W is equal to Q itself. And Q is Q in minus Q out. Q in was equal to Q in is Q1 plus Q2, and Q out is Q3 plus Q4. So W is equal to this, and hence eta is equal to Q Q in minus Q out divided by Q in. So you write this as 1 minus Q out over Q in. That is the efficiency of the engine. So efficiency of the engine, 100% efficiency means eta is equal to 1. 100% efficiency amounts to saying that no heat was lost. Whatever heat was received, it was all converted into work. There was no Q out. Q out was 0. And therefore, efficiency was equal to 1. And efficiency is equal to 0 when whatever heat was taken in was also thrown out. Therefore, no amount of work done. So efficiency goes from 0 to 1. And this is how we will measure the efficiency. Now, it is easy to see from whatever we have. Any questions over here? All right. Actually, you know, in the things that I'm describing are the seeds of the second law of thermodynamics. One statement I will quickly make. It is impossible to have Q out equal to 0. You cannot convert the entire heat into work. This is a law of nature, discovered empirically and turned into the second law of thermodynamics. And this is one of these statements of the second law of thermodynamics, perhaps worded very nicely by those people who may turn them into law, but this is the essence of it. There is another way of putting this second law, and this is in terms of what we call, here we took 2 heat baths, connected them in such a manner that in this cycle there was one heat bath at higher temperature connecting them here, and there was a heat bath at lower temperature connecting in this way. The heat was able to flow out in these directions because there was more heat in the working substance than in the heat bath. Therefore, the heat could flow out because they were at a higher temperature. And similarly, over here, the working substance is at a lower temperature than the heat bath. Therefore, heat can flow in from outside. Okay? Now, converse of this is the refrigeration cycle. In the refrigeration cycle, you take heat from a colder environment and give it out to a hotter environment. So before I do that, let me also make another statement. No, let me continue with this. The other statement that I wanted to make was it is impossible for a spontaneous process to take heat from a colder bath and give to a hotter bath. without working on it, without supplying a work. These are my words. You will find these things written in several different ways by several different people, and italicized statements in textbooks. This is another statement of the second law of thermodynamics. Says that you cannot. This is the spontaneous process is something which happens without the aid of anything else. And a spontaneous process there is a natural dissymmetry, natural, let me put this word, natural dissymmetry. Something exists in nature which gives out this dissymmetry, which lack of symmetry. Spontaneously, heat can flow from a hotter body to a colder body. But spontaneously, heat cannot flow from a colder body to a hotter body. This is something that we see all the time around ourselves, and this is what I am calling a dissymmetry that exists in nature with respect to the spontaneous processes. What I wrote over here is saying the same thing, that this symmetry exists, but you can overcome this dissymmetry. I have written two statements over here. This was sort of not copied from anywhere, so I made I shouldn't have written here because I have used the word spontaneous process over here. So a spontaneous process would be something which will occur naturally without anybody's help. And what I had written over here was saying without help again. So it was stated twice. So I'm taking out the second time. So without any help, you cannot take heat from a colder body and give it to a hotter body. All right? On the other hand, we all know that in spontaneous process, spontaneously you can take heat from a hotter body and give it to a colder body. So that dissymmetry is going to give rise to a fundamental law somewhere. Fundamental law of nature. And I'll put a question mark over here saying that this seems to be like the existence of a fundamental law of nature. We still do not know what that fundamental law of nature is, and we will wait to see what that fundamental law of nature is. Okay? This dissymmetry points to this existence of this fundamental law of nature. And what I have described up there about heat engines, and from it concluding making these statements, I was actually trying to come to describe this refrigeration cycle, which is like there is a colder bath, and there is a hotter bath. Bath in the sense of reservoir of heat reservoir, and system is here, and system is taking heat from here and giving it there, but it can't do it in violation of this law, so it will have to be some amount of work must go into it. Some amount of work must go into this, and this amount of work will help it, assist it in taking this heat, extracting heat from here and putting it there. Now that is what the refrigeration cycle is, that is what works in our air conditioners, and that is what works in refrigerators and so on. Here, again, because it works in a cycle, therefore du is equal to 0, and dw or w is actually the amount of heat that it takes in and gives off, and that amount of heat is from hot bath and cold bath, high temperature and low temperature heat bath. Heat bath is, every heat bath is, as I said in my first lecture, is an infinite source of heat, but a source of energy, but it is identified with a temperature. So it will have a particular temperature, and anything brought into contact with that heat bath will try to come into equilibrium with that heat bath, and that equilibrium will make the temperatures of the two, body and the bath, the same. So this heat bath is therefore, the temperature will be the identification of the heat bath, and therefore this is the difference between them. You know, we still do not know what heat is coming in and what heat is going out, but input heat Q in is in this case at low temperature is QL, and thus QL is coming into the system, so it is positive, and Q out is what is going into the hotter heat bath, and that is negative, and therefore W is positive. Work is done, has to be done on the system. So I have a quick, a refrigeration cycle. Any, where you think I'm not very clear? Any questions? This one? As I said, this is the temperature, this heat that is taken in from here is heat taken from the lower bath, lower colder bath, and that is the heat taken in, and that, because it goes into the system, therefore it is positive, and heat QH, which is given out to the hotter bath, is the Q out, and that is, because it goes out, it is negative. Okay?
Same, but you described as a Q in minus Q out, and here you are doing the opposite.
Yeah, I will describe this, the efficiency. Instead of efficiency, we will have, in fact, what we will call coefficient of performance. Of a refrigeration cycle. It is traditionally called coefficient of performance and written as capital K. This is the QL divided by W. How much of heat is taken in divided by how much of work needed to be done for the system to supply heat from the lower level to the upper level. And this is given in terms of, I could write this as QL over QH minus QL And hence I can write this also, I can write QL also at QH minus W divided by QL, divided by W. So I wrote the same thing here and the same thing over here using the relations of Q among Q's and W and Q. And K is also given in terms of temperatures. Temperatures of the lower bath at TL and of the higher bath is at TH. This is the performance of a refrigerator. Lower temperature divided by the difference between higher and the lower temperatures. Magnitudes was only put into to postpone putting in signatures with heat going into the system and heat coming out of the system. That was it. So say that again.
Work done is positive. So Q out is greater than Q in. Q out is greater than Q in, right?
Q out is greater than Q in, yes. Okay. In a refrigeration cycle, what happens is that you take some heat in, you add to it some amount of energy coming in from work and throw out more heat outside. Okay? I will come back to these things in a little more detail later on. I need to I will sort of check these things later on. I just described this refrigeration cycle because I was already talking about the heat engine, this engine. And since it is only the inverse of this, so it was appropriate to look into these now.
Why is this ratio equal to the ratio of temperature?
Oh, you will have to wait. I will show this later on. I also just wrote these things here, but I will come back to it.
Shouldn't the work done be equals to QL minus QH?
QL minus QH because because the work is positive, so QH is larger than QL. Okay? Because you throw out more heat than you take in. Okay? All right, now we come to a very important thing in the conceptualization of the second law of thermodynamics, and you have read about this thing in your earlier classes. I think this Carnot engine. Okay? The interesting thing is that Carnot proposed his engine, and 30 years before, nearly 35 years before the second law of thermodynamics got to be formulated. And the significance of Carnot engine came to be seen at that particular time. Carnot engine, or at times it is, cycle. There is a particular cycle which Carnot devised, and then he put forward a theorem, and he said, the cycle that I am devising, there cannot be a more efficient cycle than this. If you were to calculate efficiency, you cannot exceed this efficiency, and even this is not 100% efficient. Yeah? Say that again. मैं समझा नहीं सवाल आपको.
समझा सकते expression work done is equal to QH minus QL.
Okay, this one. There is this. Okay, there is a balance of energy. There is some heat coming in here, some energy coming in here, some more energy getting together with it, and then being thrown out. Okay? And that is the expression for the totality of energy that is being done. So whatever the difference between these two was supplied by work. Okay? Does that answer your question? Okay. Yeah?
So, but here you are kind of defining work as heat out minus heat in.
Yes, and
What you described as Q in minus Q out. So that's
okay, but you see, I am now in the refrigeration cycle. That was the heat engine.
so on which basis that we are calculating work.
Okay, here, as I said, this question that this gentleman is asking is, this seems to be sort of not quite like what we said over there, W is equal to Q in minus Q out. And here we are saying W equal to Q out minus Q in. All right? And I just answered this question. You have to see how, you see, I wrote this. For the upper one, I have the following diagram that will make you understand. That you have a heat bath here and a heat bath here and a system here, and system performs work. So you have hotter bath and you have a colder bath. Okay? It takes energy from here, performs work, and then not that in the process consumes some of this energy. Therefore, whatever is left is thrown out. So that is what is written over there. Over here, this is the process, and this will be the equation.
So the sign is opposite or we QL or QH?
This one?
Yes, sir.
No, the sign convention is the heat going into the system will be positive and coming out of the system will be negative.
QL water bath means
No, QL is lower and higher. Low temperature and a high temperature. Low temperature and high temperature. Okay? So L is for this and H is for this. Sorry, I wasn't very specific about this. Okay. So, asking questions has proved to be useful. Any more questions? Okay. Carnot cycle is very ingenious. It again has to go in a cycle, and it again goes through compression and then expansion and expansion. Here we actually also, in this particular case, this was a very specific design in which there was this expansion and compression, and no expansion either this way or this way. In the Carnot cycle, we will have compression and expansion, and 4 different. In the last, remember, towards the end of my last lecture, right towards the end, I made out a diagram for 2 things: PV equal to constant and PV to the power gamma equal to constant. Okay? And I said PV equal to constant is in the case of isothermal process, and this is in the case of adiabatic process. You remember that? And I said that PV equal to constant is the same isotherm that we drew over there in that little picture. So we have therefore isotherms going like this. And adiabatic PV curves, because gamma is larger than 1, we saw that in the last lecture. Gamma is a ratio of heat capacities, Cp and Cv, and Cp is always larger than Cv. So gamma is greater than 1, and therefore as a function of V, P proportional to 1 over P proportional to 1 over V to the power gamma, if gamma is larger than 1, then P will fall more sharply than the other case, 1 over gamma V. And therefore this falls more sharply and it comes down like this. The curve that I have just drawn is an adiabatic. So the dark blue is the adiabatic variation, schematically. You know, it will calm down. It will calm down. Just catching the echo. Okay. In this particular case, the thing that I described in my last lecture was that in this particular case, if you let the system expand from this volume to this volume, V1 to V2, adiabatic expansion takes you from one isotherm to the other. And in isotherms, we also notice that this is T1, T2, and T3, and T1 is smaller than T2 is smaller than T3, so that adiabatic expansion reduces temperature, cools down the gas, any gas. Okay? Adiabatic expansion will cause cooling. This was the result that we saw towards the end of our last lecture. I will now draw a Carnot cycle which is based on processes which are isothermal and adiabatic. Compressions and expansions which are isothermal and adiabatic. क्या हो गया? हाँ नहीं, ये मेरी गलती है कि मैं बहुत करीब चला जाता हूँ, मगर मैं क्या करूँ, वहाँ लिखना भी तो है. I will draw this picture. This time I am making so I will make these isotherms, and in these isotherms I will draw adiabats. चौक और कोई कलर नहीं है? हाँ? कलर है ना, तो लाइए ना, पीले और लाल और so here we are. ये जो dark blue, these dark blue ones are the adiabatic curves, and these are isotherms. And here I don't now need, as I see, I don't now need this one. This is at temperature T1, and this is at temperature T2, and this is good, thank you very much. So I can now draw a process that was proposed by Carnot which will be coming isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Okay? The four curves over here that I drew are from point, I will start from here, point A and B and C and D. So it has to go in cycle, so it doesn't matter which point you take as the starting point. Our starting point is point A, and then it goes to point B and then C and D, and then back to A. And in this particular process, you can see that A to B is isothermal expansion, B to C is adiabatic expansion, C to D is isothermal compression, and D to A is adiabatic compression. Okay? So you have therefore these four processes. And these four processes, the basis for proposing this is this, that for isothermal process, pressure is proportional to 1 over V. For adiabatic process, pressure is proportional to 1 over V to the power gamma. And therefore the slopes of these two, isotherms and adiabats, are going to be different, and because of which you have the possibility of generating this particular cycle. This is what Carnot proposed. How do you visualize implementing this on a machine? This can be seen in the following manner. You start with a container. This container has walls that do not allow heat to go anywhere. You connect it with a heat bath at temperature which we call TH, high temperature heat bath, and let the and this is there is a piston over here. These lines will indicate that system will not be able to exchange heat through these walls, and you put some weight on top of this. I am putting this weight in the form of some kind of weight, okay? This weight. So it starts with pressure P1, volume V1, and temperature TH. The point A, at point A, you connect it to a heat bath at temperature TH. Now, next, what you do is, again I will need to draw this thing, you reduce pressure. How do you reduce pressure? You take away this weight slowly from here. When you lift the weights slowly, gradually from here, you slowly let the pressure go down. You are coming down from point A to point B. You are reducing pressure in that particular process. And because you reduce the pressure, the volume will increase. So this is point A. And reduce P, V1 increase, V increases, volume increases, heat enters the system because it is connected to the heat bath, and because it is an isothermal process, TH remains TH. Temperature doesn't change because it is going on an isothermal path, and because it is continues to be connected to a heat bath. And as long as the body is connected to a heat bath, its temperature will remain the same. कोई सवाल है इधर से? Okay. I should do that. Okay. Next. So when you have done this, you end up by getting into a position where you have a heat bath here at TH, and you have lifted weight, so the amount of weight on top is smaller than before. Okay, and your P is P2, and volume now has increased to V2 in this case, and QH amount of heat has entered into the system, and the temperature of the system remains at TH. Is it too small again? It is? All right. This is where you reach point B. Now I will try to be make it a little bigger system. After that, what you do is you take away heat bath and put an insulator at the bottom. Put the gas on, so that this now is a situation of a adiabatic process, ready for an adiabatic process. You take it away, you take out this heat bath and put here an insulator, so that the entire gas is completely enclosed in insulated environment, and you will now, because you further reduce further reduce weight, so lower pressure. So you end up, now I'm going to make a bigger diagram, doesn't mean that the system has grown in size, just because those people at the back ought to also be able to see this. So you have therefore a situation where the bottom and sides are all insulating, and the system has further expanded. The weight on top is even smaller now, okay, and the pressure at this point is P3 and volume is V3, And because now it has been an adiabatic expansion, therefore T has gone down with less than TH. The temperature over there was hot, the temperature of this bath. The bath has been removed, and then the gas is allowed to expand. So the temperature would be T3, which will be less than TH. The gas will cool down. It is cooling down, it is coming down now to reach the point C. This is reaching point C. It has come down from temperature T2 to temperature T1. I have called it temperature T3 for some reason. Okay? So I will call it temperature T1, so that it has come down from temperature T2 is, this is T2 is the same as TH. T1 is less than TH. And then again from here I will perform another task. I will now increase pressure. Put back weights, add pressure, the volume will decrease, and then connect to a heat bath at lower temperature, at T1. So here you have now this system. Here you have a heat bath which is connected at temperature T1, and I call it TL also. And because I have put in more weight on top, I will push down the piston, and the volume will be reduced. And this is when by reaching point D. And from point D to point A, you will further add to this, but then take away this heat bath and again put an insulating sheet below, like you did in this case, and you will get back to point A again. Okay? So what I have been able to do so far has only been to describe how Carnot engine works, not beyond this. What remains to be done is to show that this is actually a very efficient way of working. Not just very efficient, but the most efficient engine that one can think of. And that this also allows us, I'm doing this because this allows us to actually get closer to defining what entropy is. So in the next lecture, we will complete the discussion on this, whatever remains, and then I will also, today I had some pictures of showing you how heat engines work. I will take this up day after tomorrow.
You're not doing this.